On to delta H method number 3, using Hess's law. So here's the textbook definition for Hess's law, but let me give you a better explanation using an analogy that'll hopefully help it make some sense. So let's imagine two people who want to climb a mountain. One's a, extreme hiker, death march style, and they're going to get to the top of the mountain and they just walk straight up to the top. The other person, they like a leisurely hike, so instead they kind of slowly loop around the mountain. And so they take their time getting up there, but eventually they make it to the top as well. So then the question is, who went higher? Whose change in height was more? The answer is both of them. So even though this person went up faster, they got to the same height as this guy. So both of them had the same change in height. It doesn't matter what path you take to get there. It just matters where you wind up. And that's what Hess's law says. So if you do a reaction as one solid step, or if you do it in a series of steps, but you wind up with the same products, you're going to have the same change in energy. So it really doesn't matter how you get there, as long as you get there. So to make this point, here's two different equations. So the first one shows nitrogen dioxide producing nitrous oxide and oxygen. The second one shows nitrous oxide reacting with oxygen to form dinitrogen pentoxide. And the first reaction is endothermic, and it requires 228.4 kilojoules of energy. The second reaction is exothermic and releases 447.4 kilojoules of energy. Now, what you probably notice from this reaction is that nitrous oxide and oxygen are the products of this reaction, and they're reactants in this reaction, which means that really these two could take place in the exact same vessel, which means that we can actually sum these together to come up with a brand new reaction. So it looks like nitrous oxide, NO. We've got 4 that were created, then 4 that were used up. So overall, it didn't really exist. If it's created and destroyed, and the net reaction doesn't happen. We also have 2 oxygens that are created and then 3 that are used up. That means that the 2 that were created are both going to be used, and we're going to be left with just 1 oxygen on the reactant side. And so overall, our net reaction could be 4NO2 plus, sorry, I'm going to turn that into a giant plus sign, plus O2 turns into 2N2O5. So we can call this step 1 and step 2. And if we did this reaction as step 1 then step 2, well, first we'd have to put in 228.4 kilojoules of energy, and then it would release negative 447.4 kilojoules of energy. So overall, how much energy change would there be? What would the overall enthalpy be? Well, you just add those two together. So here we see a series of steps that wound up being just this overall reaction. And whether we did it as this step followed by that step, we would wind up with a net change of negative 219.0 kilojoules of energy. If we just do it as one straight up step, so march right to the top from NO2 to O2, we would get the same change in enthalpy. So that's Hess's law. We can figure out the overall change in enthalpy by looking at the individual steps that might be used to create this overall product. Unfortunately, it's not always quite that easy. Shocking, right? So, for example, let's take a look at this problem. We're going to try and figure out what the change in enthalpy is for changing carbon and hydrogen into propane, C3H8. Now, here is our series of steps that we can use. We see here we've got propane reacting with oxygen to form carbon dioxide and water. So that's a combustion reaction, and as we can expect, it's got a very, very exothermic enthalpy. And then some other steps. Here's our water formation from hydrogen and oxygen, and also carbon and oxygen forming CO2. Now, if you look at these, there isn't really a way to sequence them to equal that as they stand. For example, in this reaction, we've got propane as a product, but over here we have it as a reactant. We've got hydrogen gas as a reactant, so that's okay. But we're not going to be able to just order those straight up and cancel things out. We wouldn't get what we want to get. The same rules apply. We just got to kind of blaze a new trail. So instead of using the reactions just like they stand, we're going to have to change them to make them match our equation. Let's start with the easiest one, which would be the propane reaction number 2. So we see here that we have propane reacting with oxygen to form CO2 and water, and it's releasing about 2,000 kilojoules of energy. doesn't match up with this because we have it here as a reactant and over there as a product. So the solution for that is flop the equation. Make propane a product instead. I know what you're saying. Mr. Jones, you can't do that. You can't just flop an equation around. Well, yes, I can, as long as I account for it in my delta H. So the change in enthalpy for this reaction right here is going to be different than that reaction right there. When we combust C3H8 with oxygen, we generate 2,000 kilojoules of energy. However, if we wanted to react CO2 and H2O to produce propane and oxygen, we would have to supply it with that much energy. Writing a reaction this way is like rolling a ball down the hill. Gets to the bottom of the hill, it's released energy. And it's not like at the bottom of the hill we can never get it back up to the top. We've just got to push it back up to the top. And we'd have to supply in the same amount of energy that it released rolling down. So if we're going this way, we're pushing it back up the hill. And so it's not going to be a negative enthalpy, it'll be a positive. So we would have to put in a positive 2,220.1 kilojoules of energy. And there we go. We now have propane as the product that we want it to be. Now we've got to take these other two equations and find ways to get them to fit in as well. You can see with reaction number 3 we have carbon as a reactant, which matches up there. However, this reaction only has 1 carbon, and that one has 3 carbons. So what do we do with reaction 3 then? We triple it. And if we tripled the reaction, how much energy would we produce? Triple. So if 1 C plus O2 yielded 393.5 kilojoules of energy, then 3 moles of carbon plus 3 moles of oxygen would yield 3 times negative 393.5 kilojoules of energy. And then finally, let's deal with our first equation that gets us hydrogen. Right now we have carbon for our reactants, but we don't have any hydrogen on the reactant side. So we have to use that top equation. We see here this one yields 2 hydrogens, or uses 2 hydrogens, what we need 4, so we're just going to double that reaction. And so then once again we would double that delta H. So at this point we can now go to the sum together step, and we can sum together also our delta H's to figure this out. So let's check and make sure that we've wound up with what we want to wind up with. So we can see here we have 3 CO2s that were used and then recreated. So overall CO2s were there and then they're there at the end, so no change there. It's not part of the reaction. Waters, let's see, we have 4 H2O and 2 H2O right there. But of course that H2O right there should be 4. I forgot to double my waters. And that makes it so they both cancel out. And then let's see, we have 3 oxygens there and 2 oxygens there, so a total of 5. That'll cancel out those 5 right there. And what we are left with then that will no longer cancel out is 3 C's plus 4 H2s yields C3H8. So we just generated our equation that we wanted to start out with. So now we want to figure out what the change in enthalpy is for that. We would, same way that we added those together, we just add together our enthalpies. And what we wind up with is negative 103.8 kilojoules of energy. So that means this overall reaction would yield this much energy, and it is exothermic, so that would be energy that is released from this reaction.